Okay, at the start of the chapter, I mentioned that there are two types of spread models we're going to discuss in this chapter, right? And in section 5.2, we discussed a lot of models, and they were models based on percolation theory, which means that they focus on the nature of the media, um, the environment of the spreading phenomena, right? And in section 5.3, which is the section for this video, we're going to talk about growth models. They focus on dynamics of the spread process itself, instead of the environment, instead of the media in which the spread is happening. Okay, so let me jump to section 5.3. Okay, the very basic growth model I want to start with is called Eden growth processes. Okay. So growth by random accumulation of material on the boundary of clusters. For example, this type of models can be used to simulate the bacteria colonies, tumors, urban fringe, invasive species. Okay. And a simple model with many variations, but the very basic version of Eden growth process should follow these steps. Okay, first step, start with an initial seed. Usually we put this seed in the center of on the center of the lattice, and then randomly select one unoccupied neighbor, okay, of an occupied site. So at the very beginning, only the central cell is the occupied site. Okay, it's a seed. It's the first site that is occupied. Okay, which means that the first step is choose one of the unoccupied neighbors of the seed and occupy it. Right. Step 3, occupy it, and repeat steps 2 and 3. So you can imagine that at the very beginning there is only a seed. So after the first step, one other cell or one other site will be occupied. But at step 3, since we have 2 occupied sites, right? So the candidates for the next step to occupy increased, right? Because now we have 2 occupied cells, 2 occupied sites, right? So you can imagine that this process is going to be faster and faster. So this spreading process is accelerating in terms of the speed. Okay, on the right side is an example. It's a type of Eden growth model. It's called diffusion limited aggregation. Okay, I'm going to introduce it later, but the very simple version of Eden model can be found here. Okay, model 5.7. So what's the properties and what are the dynamics we care about Eden growth? Okay, so properties: compact and dense interior with a diffuse and this a crenellated parameter. Okay, on the right side we have a simulation result from model 5.7, and you can see different sites, they are colored, they are painted by different colors. So the pink part, the pink part is full of sites that were occupied a very long time ago, because this growth started from the very center of the lattice, right? Then the white sites, then the blue sites. Blue sites, they are sites occupied recently. And all those red pixels, or you can say red sites, they are what? They are the parameter of the spreading. Okay, new occupied sites, they are going to be selected based on these red sites, because newly occupied sites after next step will be chosen from the neighbors of these red sets, right? So dynamics, what we care about this Eden growth process. How does the geometry emerge over time? Okay, and what are the scaling dynamics of the active zone of the front line of this spreading of this growth? Okay, so we care about these dynamics, and we can just use several figures and the plots and the curves to address that. Okay, so this is a basic Eden growth process at 5,000 at 5,000, 10,000 and 20,000 steps. Okay, actually it starts from 2,500, right? 2,500, 5,000, 10,000, and 20,000. So on the left side, we have four figures showing you actually the spatial pattern of the colony of the growth. On the right side, we have a plot. We have a pattern showing you the relationship between time and parameter length. Okay. So at the very beginning, when the time is equal to 2,500, from 0 to 2,500, we can see that the length of parameter increases rapidly, because you can see that this curve here is very steep from 0 to 2,500. And when the tick arrives at 5,000, you can see that the parameter continues to grow, continues to increase, but the speed is slowing down, because if you compare the first half of this curve, it's very steep, but the second half of the curve from 2,500 to 5,000, the steep it's not that steep anymore, which means that the slope decreased a little bit. And as this colony increases, grows, you can see that although the parameter length increases accordingly, but it increases at slower. It increases slower, and its increment gets slower and slower, because the slope of this curve decreases dramatically, right? So here, when we're talking about the spatial pattern after 20,000 steps, you can see that this curve is basically flat. The slope is very close to 0, which means that if you continue to run this model, right, at 30,000 steps, 40,000 steps, pretty sure that the parameter length will still increase, but it will increase at a very low speed. Okay. So this figure, this huge figure here, shows you the change of spatial pattern of Eden growth as the time passes by, and also the change of parameter length by time. Okay, and we have a more complex version of Eden growth that I want to introduce. Is called noise reduced form. Okay, unoccupied site must be visited a certain number of times before it becomes occupied. Reduces random error but slows growth. What does it mean? It means that if there was no noise reduction, if a site is unoccupied and it has been chosen to be invaded after next step, then okay, after next step, this unoccupied site changes to occupied. But if you add noise reduction into this simulation, you can assign a specific number for visiting before an unoccupied site can be occupied. For example, if you assign 3 as the visiting time, number of visiting time, a specific every unoccupied site needs to be visited for 3 times to be occupied. What is this? This is a process to reduce random errors. For example, there is a new restaurant nearby, right? You want to try it, but you don't know if it is good. Okay, so the first time you go there, maybe by accident, or you just want to try it. But as a result, you may think, okay, it's good, I will return. But if the food there is pretty bad, you don't want to come back, you can consider this first visit as a random error. It's something you have to accept to test if that restaurant is good, right? So if you have visited for the first time, it's good. You go there for the second time, still good. The service is good. The food is good. You will visit this restaurant for the third time, for the fourth time, then you know this restaurant is pretty good. You go there regularly. Then you are sure that there is no noise about this restaurant because you have tried it, you have visited it for several times. Okay, so it's reliable. It's the same idea here. Okay, unoccupied site must be visited a certain number of times before it becomes occupied. Of course, the larger this certain number is, the more stable your simulation will be. The more stable this process will be. But you should know that the higher this certain number is, the longer it will take, this growth process will take to spread out. Okay. So here, simple Eden growth with no noise reduction. We just use the revisit time, a number of revisit is 0 here, right? There is no noise reduction. So M is the number of visiting time before occupying a specific site, right? So this is the spatial pattern. And when you change this M value from 0 to 10, which means that before occupying a specific site, you need to revisit this site for 10 times. So this is the result. If you compare these two spatial patterns, you will see that the second one, the boundary, the parameter of the second one is smoother. Okay, because all those sites occupied, they were not occupied by accident. They have been visited many times to make sure that there is no noise. Okay, and if you compare the central part, the pink part of these two spatial patterns, in the top, in this top figure, we can see that there are a lot of small white noise inside this pink part, but less noise can be found in this figure, in this spatial pattern. Okay, you can consider all those white sites, they are noise, and they have been reduced after this noise reduced process of Eden growth. Okay. And we can use Eden growth model to simulate a lot of real world phenomena, right? Firstly, we can, for example, we can use it for epidemic, for the spreading of a disease, okay? When new cell is selected, unoccupied cell is selected, it becomes occupied with a probability P. In basic Eden model, if one unoccupied site is selected, then it is occupied for sure. But here, it's not for sure. There is randomness. It is occupied with a probability P, which means the cell is ill with no chance of subsequent recovery. Once it is occupied forever. Okay, or becomes unoccupiable with a probability 1 minus P, which means that this cell will never be occupied, which means it becomes immune to this disease. Okay, so you can say here how Eden growth model has been applied to the spreading of disease, right? right? With a probability P, an occupied site will be occupied forever. But with a probability of 1 minus P, this cell will become invincible. There is immunity. With a probability of 1 plus P, a cell will get immunity, which means it will never be occupied. Okay? There is a critical value of P that is the same as the percolation threshold in ordinary percolation models, which means the PC value is equal to 0.573, I remember, right? Here is a model. You can play with it a little bit, and you will see that there is huge change in terms of spatial pattern when your p-value is very close to PC. Okay, make it lower than PC a little bit, make it higher than PC a little bit, and you can see the change. And we can also use Eden process to simulate the growth of urbanized areas. Okay, 5.14 is for that. It's a variation on noise-reduced model. Firstly, site must be visited p times to be occupied. This is a very basic noise reduction model, right? But adjacent sites to a visited site are added to list of potential sites. It means that, for example, site A has been visited for the first time, but you need to visit site A for 10 times to occupy it. But if we are using this urban growth model, all those adjacent sites to site A, they can be visited even they are not adjacent to an occupied cell. Okay, so A can be a secondary seed. A is adjacent to an occupied cell, right? But when A is visited for the first time, even A has not yet been occupied, its neighbors can be added to the list of potential sites. If for some reason, luckily, one of A's neighbors are visited 10 times before A, it means that that neighbor of A will be occupied first before A is occupied. Okay, so that's for the urban growth model. So simulates two aspects of urban growth. Firstly, the central region, downtown of many cities, is compact. Okay, this is actually the result of the first rule here, the very basic rule of noise reduction model. Site must be visited p times to be occupied. These sites, they will form the core of the city, the downtown of the city. And the cities are not one continuous cluster, but often a main central cluster surrounded by a large number of much smaller clusters. This is implemented by the second row of the model, okay? It means that the example I mentioned before, set A, right? Although set A has not been revisited, say, 10 times, but one of its neighbors has been visited for 10 times. It means that that neighbor will be occupied, will be a part of city, but A has not been a part of city, because A maybe has only been visited for 8 times. So you will see that there is a gap between central city, between downtown, and that newly occupied neighbor of A. And A is that gap. Okay, you can imagine if this situation is happening many times, there will be many gaps between downtown, between the center of the growth and other small clusters. Okay, so that's how this model is trying to address the multi-center spatial pattern of urban areas. It's very common in real world, right? Columbus has is a huge city, right? And it has a downtown area, but there are other small cities surrounding Columbus. These small cities, they have their own small downtowns, right? And before these small downtowns and the big downtown of Columbus, there are other areas, rural areas, or not very well urbanized areas. They are like the gaps between clusters. Of course, the downtown of Columbus is the largest cluster, and there are small clusters who are used to address small downtowns of small cities surrounding Columbus, right? So this is model 5.14. It's very interesting. You should go there and try, okay? And also, we can also use a Eden process to address the spreading of invasive species, okay? 5.15, Eden process along a line. It's just like 512, but with sporadic long distance dispersion. Okay, let me show you. Yeah, it's here. 515. Let me say, let me reload it. Okay, set up and revisit time. Let's just change it to 10. Okay, a site, an unoccupied site needs to be visited for 10 times before it can be occupied. Okay, let me set up and go. Okay, it's too much, I think. Let me change this to 1. Okay, here is the result. It's still not too obvious. Let me try normal distribution. Revisit time 0. Okay, now it's very obvious, right? So you can say that this invasive species starts to grow from the bottom of the lattice, and it is growing to the top of the lattice. Okay, and this is a line invasion because this program will make sure that the height of all those pixels, they are generally within a range. Okay, so obviously we have a front line, a very convoluted front line of growth here, right? But the program is making sure that the difference of height between different sides along this front line is not too huge. Okay, let me say, I'm trying to find a very typical spatial pattern here. Okay, this one is more typical, right? So color by time. Okay, although like I said, this program is trying to make sure that this front line is not too convoluted. It's convoluted, but it's not too convoluted. But here it is different. This model for invading species is different from the pure line invading or pure line growth process, which is 5.12. In this model, in 5.15, there is what? Sporadic long distance dispersion, LDD events. What are they? Can you say these small clusters jumped very far away from the main cluster? Can you see this small island on the right side? Let me make it larger. Go there. Larger. Can you see right here, this island and also the small clusters, they are LDD, which means that with a probability, with a specific probability, some sites that are very far away from an occupied site, they can be chosen by the program and occupied after they are visited here for 5 times, which means if they have been visited 5 times and then there is another visit, then they can be occupied. So here, right, we have some small clusters away from the main community, main colony. It means that sometimes invading species, they may leave their huge community, and for some reason they can travel further away to form a smaller cluster away from the main community of this species. Again, I use different colors to paint different sites occupied at different time, right? Pink areas, they are sites occupied long time ago, than white sites, than blue sites. Okay, obviously, you can use different distribution modeled using probability distributions to decide the distance of this LDD. Because if it happens, it means that another cell that is far away from an occupied cell will suddenly be visited for some reason. But how far away? What is the distance I should use when this LDD is happening? You can choose a distance from different probability distribution, normal, exponential, or Cauchy distribution, right? Okay, so that's another application of Eden process or Eden model, okay, for invasive species. Okay, there are other literature using Eden process as basic as the foundation, and use it to address different issues and problems in different realms. For example, this one, inverse Eden, okay, and is for epidermal wound healing. Okay, start with a hole in the middle of the lattice that might be an injury on your skin, a wound on your skin, and infill from edges using rules as above, right? Classic model. This model is trying to address the process of your skin, which is trying to heal itself. Okay, and another very interesting one is for epidermal tumor cell spread. It's a spread of tumor cell, right? And in the model library of the textbook, we have several other models, a variation of Eden models, Eden growth models. If you're interested with them, you can go and play with them and check the code and say what they are trying to do. Okay, so this is the end of this video. I will see you in the next one. Okay, thank you.